Hi, welcome to Illinois Groundwork. This is a web-based resource that contains research and tools to help optimize the design and planning of green stormwater infrastructure in communities and cities. My name is Mary Pat McGuire. I'm an associate professor of landscape architecture at the University of Illinois, and it's my pleasure to introduce to you one of our collaborators on the research that informs much of the toolkit, Dr. Rajmina William. She is a civil engineer, and she's going to talk through what reliability curves are, why an understanding of reliability is really important in the face of climate uncertainty, and what are the different variables that go into increasing the reliability of any designed green stormwater infrastructure.
Thanks for that kind introduction. And as Mary Pat mentioned, I'm here today to take you under the hood and talk about some of the science behind the tool. And specifically, I'll be talking about the concept of reliability curves and why we use them in so many of the design calculations that underline this tool. Before we talk about reliability curves, though, let's take a step back. The first thing you probably notice that's a little unusual about the tool is that we talk a lot about probabilities. Well, why is that? Well, uncertainty is an important part of how we design green infrastructure. There are some uncertainties that we can't control for. For example, the types of storms that our infrastructure might experience, or the natural variability of our underlying native soils to infiltrate water. We can also have uncertainties in our design parameters. So for example, the exact porosity of the soil medium that we use in planting will always be slightly variable. We characterize those uncertainties using something called a probability distribution. And this is just a way of characterizing the overall probability of the spread of a given parameter. Some of these distributions can change over time. So think about what happens when your rain garden gets clogged, for example. Your infiltration capacity of the soil will go down as it gets clogged, so the probability distribution of that infiltration capacity will shift to the left. We capture the impact of all of these changing uncertainties on our green infrastructure performance using what's known as a reliability curve. And reliability is simply the probability that a system will successfully meet a target or goal. And I'd like to take a step back again and make sure that we understand that it's important that success could mean a lot of different things to a lot of different people. Some communities might be interested in the ability of green infrastructure to improve water quality, while another community might prioritize urban heat island. Because in this project, we are interested in flood management. In the context of the simulator, success is the ability to reduce the volume of incoming runoff by a specific percentage. And for the GSI sizing tool, we've chosen a threshold of 80% reduction. So reliability curve, as I mentioned, plots the reliability of success against the magnitude of the storm. As the size of the storm increases, the probability of our system successfully capturing that desired volume of water, in other words, our system reliability, goes down. The duration of the storm also matters. So a short duration, high intensity storm that drops a lot of rain in a very short period of time will lead to lower green infrastructure reliability than a high intensity storm that drops a lot of rain in but a longer duration storm of the same magnitude that drops that same amount of water over a longer period of time. We can increase our system reliability even for larger storms by changing a couple of design choices. Firstly, we can increase the size of our green infrastructure compared to our upstream runoff producing area. This comparative size is important not only for system reliability, but for long-term maintenance because systems that are undersized tend to clog a lot more quickly. If there is no space to increase the size of our infrastructure, we can always try to deepen our storage layer. And that allows our green infrastructure to infiltrate and store larger volumes of water before they overflow, thus increasing our reliability. And finally, the type of soil where we choose to place our green infrastructure is also important. Generally, more sandy soils defined in our simulator as coarse soils, will have a higher reliability than soils with more clays and silts. The big takeaway is that green infrastructure uncertainty is important in design, but by tweaking a few key design choices, we can help to manage that uncertainty. Use the GSI sizing tool to explore how changing the footprint, depth, and soil type for green infrastructure in your neighborhood impacts the sites of storm you can reliably manage. We hope that the availability of these research and these tools are useful for you in managing stormwater to meet your community's goals and needs.